All right, so yeah, welcome everyone to the 2023 NeurotechX Student Clubs competition. It's an exciting time today, and yeah, let's get started. So just a few housekeeping things before we get started. Please keep your mics muted during our presentation, but as we mentioned, we encourage you to turn your video on. We'd love to see everyone's faces. You know, we'd obviously love to be in the same room right now and have this in person, but we'll have to settle for this for now. So feel free to turn your cameras on. Also, feel free to use the chat for any questions or comments. I know a few of you have already been doing that, but keep it going. And another thing I wanted to mention, we'll be sending out a survey shortly after today's award ceremony. So we ask that you please fill it out. It should only take a couple of minutes to do, but it'll give us an idea of how we can make our events even better in the future. So we appreciate that. All right, so I see a bunch of familiar names and faces here in the audience, but for the newcomers, we'd like to briefly outline some key points about NeurotechX in general. So for those of you who are a little less familiar. So we actually started out in 2015 in Montreal, Canada, and since then we've grown a lot and we've become we have more international presence. So NeurotechX, we're an international community of neuro enthusiasts, and we facilitate the advancement of neurotechnology. And actually, NeurotechX is the world's largest global nonprofit neurotech organization. And we're in Canada, but we have a presence all over the world with over 18,000 members worldwide. And as you probably know, NeurotechX was born out of hacking and community events. And being a nonprofit, we rely heavily on our amazing supporters. So individuals like you, but also other key players in the industry. And since we're a leading voice in neurotech, we use our platform to give back to the community and provide visibility to our partners with the goal of promoting neurotech as well as building trust with our global neurotech community. And at Neurotech, our three pillars are really central to our vision and how we operate. So the first one is community. So we bring people together. So whether that's events like today, or hackathons, or online forums, we're a connector of our amazing community that each and every one of you are part of. The second pillar is education. So we strive to educate our community. So we do this through our various resources, be that educational, scientific, or hands-on. We want everyone to be able to develop their technical skills no matter what stage they're at in their career. So we want learning to be accessible and barrier-free, and most of all, inclusive. And our third pillar is innovation. So we believe that once people are connected together and we're educated, we can go on and take on new challenges and create new things. And so this can be in the form of starting a new business, joining an existing company, things like that. So we really hope to inspire our community to push the forefront of what's possible and keep driving innovation. And as I said, being the largest international neurotech community in the world, you can imagine we're in many different places. Our chapter initiative has over 20 different chapters. We've collectively had over 250 events worldwide. And our number of, it keeps growing. Right now, we're over 18,000 neurotechnology enthusiasts, but we'd like to keep growing. So this year alone, we've added 4 new student clubs, and we hope to keep the momentum going and have even more student clubs and chapters join our awesome community. So we're happy to welcome the new student clubs to today's event. I see a few of you are here, so that you can kind of get a flavor of some of the amazing projects that our student clubs put out, and you too can be a part of and get a chance to compete in next year's event. And so at NeurotechX, we drive impact through innovation. So since we have people with so many different backgrounds who are at different stages in their career, we use this to all our mutual benefits. So we have undergraduate students such as many of yourselves, graduates, professionals, researchers, investors, etc. And so everyone's able to grow their network, learn new skills, work on new projects, so that you can do things like join a neurotech company or start your own company, get involved in various initiatives and tackle new challenges. And neurotech companies and startups are constantly engaging with NeurotechX, and professionals and researchers support our connected ecosystem. So we're a tight-knit community, so feel free to reach out to a lot of our members on Slack, things like that, and we're always happy to discuss new ideas and potential future endeavors. And so just briefly, at NeurotechX, you can imagine we hold many different events throughout the year. But we have 3 flagship annual events. So the first is our yearly Buzz and Review, which is held at the start of the year. This is where we present key neuroscience and neurotech news and milestones from the previous year. And then we often invite experts in the field to give talks about some of the amazing work that's been going on. The second one is our annual student club competition, which I'm sure almost everyone is pretty familiar with, since today's the award ceremony. So we have student clubs work as teams from universities across the globe and other institutions to compete by working on a neurotech project, which they submit to be scored by our expert panel of judges in the field. And we always have such amazing projects, and we can't wait to showcase some of them today. And another one that's coming up is our global hackathon. It's expected to draw in over 1,000 registrants this year. So this will be held towards the end of the year. And definitely stay tuned to our social media for more information if you'd like to be a part of that. All right. And yeah, I'd like to focus a little bit more on the Student Clubs initiative so that we're all on the same page. So what exactly are the goals of our initiative? Well, neurotechnology has never been this accessible before. And what we are trying to do is catalyze the interest and involvement of students to develop their skills by providing them with precise goals to work towards with these projects, as well as the resources they need to get there. So we want to promote research across disciplines for undergraduate students across the globe, which is why our competition is open to all neurotech undergraduate clubs. And then in collaboration with our partners, we provide resources to students so they can start their own clubs at their schools. And our goal is essentially to provide educational content to keep the momentum going. So the NTX Student Club competition, we'd like to promote collaboration. We hope that we're preparing students for careers in excellence in STEM through things like self-learning, knowledge sharing, and practical experimentation. And you'll see a lot of these things come up, especially in this initiative. So we basically believe that neurotechnology is key to better understanding and improving who we are. So we aim to inspire the next generation of neuroengineers who will be equipped to drive the field forward. And essentially, we want to make neurotechnology accessible to all. So join us in supporting students exploring innovative neurotech related projects. And here's a throwback to our first NTX Student Club demo day in 2016. And yeah, we've definitely grown a lot since then, and we want to keep growing. So for the actual competition, the requirements are all teams must submit a 10-minute video where they present and demonstrate their projects. So showing the viewers what problems they're working on and exactly how they tackle it. And they also need to submit a public repo of their code on GitHub, which describes their projects and outlines the code they used to make it accessible to everyone else. Because our biggest thing is that we want to make all projects reproducible. So that's actually one of the requirements. All projects need to be reproducible and open source. And this is, back to one of our pillars. We believe that sharing knowledge is important, and this fits in line with, who we are and what we do. So I'd like to just do a quick shout out to last year's winner, Waddle from the University of Waterloo, for their work on their SSVP speller, as well as the 2020 winner, McGill Neurotech, for their EMG keyboard project. And you can check out these videos, projects, if you check out our NeurotechX YouTube channel. We have playlists for all this, and we also have that again for this year. And so, as I mentioned earlier, being a nonprofit, we rely largely on help from our amazing supporters in the neurotech community. So we like to give a special thank you to this year's Student Club competition sponsors, who, without their awesome support, we wouldn't be able to hold this event. So this year's Student Club sponsors are OpenBCI, Neurable, GTech, NTX Services, and Emotive. Thank you. This is all possible because of your support. So OpenBCI. OpenBCI has been building open source tools for biosensing and neuroscience to progress human-computer interface technology. So their hardware and software products allow people to get a better understanding of the human body and mind. And OpenBCI works to ensure that neurotechnology is adopted into the consumer landscape in an ethical way that protects user agency and mental health. And OpenBCI also graciously provided student club teams that were limited by hardware this year with some amazing devices to support their project development in this year's competition. So we'd like to say thank you to OpenBCI. GTech Medical Engineering. creates state-of-the-art brain-computer interfaces and neurotechnologies used by hospitals and universities all over the world. GTech's hardware and software spans various domains, including brain assessments in things like brain injury and disorders, motor rehabilitation, DBS, brain mapping, neuroprosthetic control, as well as both invasive and non-invasive BCI experiments. So we'd like to say thank you to GTech. Neurable. Neurable is building the infrastructure for BCIs to live in everyday devices, so bringing the power of the brain to new markets, opportunities, and users. And some very exciting things to come this year from Neurable. So thank you, Neurable. Emotive. Emotive is a global leader in wireless neuroinformatic technology, specializing in innovation of human brain research. Emotive's EEG platform, paired with their machine learning algorithms, has been validated in over 19,000 publications in health, education, consumer, and other research. So we'd like to thank you, Emotive, for your support. And our other sponsor for this year's competition is NTX Services. So NTX Services is the exclusive partner of NeurotechX, which brings neuroscience, technology, and strategy experts together from a variety of professional and academic backgrounds. So if you're looking for consulting and recruiting from commercialization of your neurotech, be sure to contact NTX Services. So thanks, NTX Services. And next up, I'd like to just quickly outline our judges for this year's competition. So first up is Shirley Zhang from OpenBCI. So Shirley oversees the logistics behind OpenBCI's mission to democratize tools for biosensing and neuroscience. She's a biomedical and mechanical engineer who's applying her interest in scalable systems and manufacturing pipelines towards BCIs, so helping them to be more accessible to all. So thank you for all your support, Shirley. You've been a great help for our competition. Next up is Dr. David Stanley from Neurable. So David is a computational neuroscience and machine learning engineer at Neurable. He develops machine learning algorithms that translate brain activity into practical insights to help people gain a better understanding of their cognitive states. So thank you, David, for all your support. You've been an amazing supporter of this year's competition. And our third judge for the 2023 competition is Dr. Christoph Guger from GTech. So Christoph is the CEO and co-founder of GTech Medical Engineering, which develops high-performance brain-computer interfaces and neurotechnology. He oversees the global use of GTech's products for invasive and non-invasive recordings for research and clinical purposes. So thank you, Christoph, for your support. You too have been a great help in our competition this year. And we couldn't do this without our amazing panel of judges this year. All right, so next up, we'd like to announce our prizes for this year's competition. So as many of you know, this year we decided to make our competition a little bit more inclusive by having a more general theme. Last year was a little bit more focused, but this year we opened it up. So as long as your project incorporated the use of neurotechnology, then it would qualify for this year's competition. So teams were evaluated on technical aspects of their project, their video, reproducibility, and project timelines. So let's take a look at this year's prizes. So for the first place grand prize winner, the winning team will receive a Unicorn Hybrid Black Bundle from GTech. So this is a high quality wearable 8-channel EEG headset for BCI applications to acquire brainwaves. Amazing. And as well, the first prize team will also receive a 1-hour product consultation with NTX Services to discuss the potential commercialization of their project. So that's for the first prize winner. For second place prize, running up team, they will receive a GTech Unicorn Hybrid Black Bundle 2, which is, again, a great EEG device. And for the third place runner-up, they will receive an Emotive Insight, a 5-channel wireless EEG headset that's pretty easy to use, as well as Emotive Pro for a year of use. So that's amazing to the third place team. And so this year's prize category also included an additional dimension, neuroethics, where teams were evaluated on this aspect of their project, addressing how they would ensure that the output of their work would be used in an ethical way and ensure a better future. So what are the risks involved with this and how will they mitigate them? And as we know, this has become recently an even hotter topic, and it's always been an important aspect of research that's come into light. So the top scoring team in this category will receive 3 Neurable yet to be released N10 early access headsets at the end of the year. Exciting. Okay, now that we've gone over the prizes, the last thing that we need to just introduce is, of course, our amazing student clubs. So this is the roster of the 2023 NeurotechX affiliated student clubs. And we have, again, clubs from all over the world. This year we had over 25 active clubs, which is great. And like I said, we're always adding new clubs, and we hope that next year we'll have even more active clubs. So be sure to register for next year following this year's award ceremony. And so we had over 25 clubs, but we had over 20 proposals outlining what the student teams plan to work on from these clubs that you can see here, which was great. And we got some amazing proposals, and we're really excited to see what you guys plan to work on. And in the end, we had, in the summer when we opened up submissions for the final projects, we had 9 teams that submitted final projects to compete amongst each other. And the teams that submitted these final projects are Neurotech UCB, Triton Neurotech, Johns Hopkins Undergraduate Brain Computer Interface Society, Neurotech at Davis, Neurotech UMSA, Neurotech at Rice, Maction Potential, Neurotech SC, and Neurotech U of T. And like I said, to see these amazing project videos, please check out our NeurotechX YouTube channel for the playlist, and you can check out all the amazing projects that were worked on for the 2023 competition. Okay, so now is the moment I'm assuming everyone has been waiting for. We'd like to start with the 3rd place prize, which is, like I said, from Emotive. It's the Insight with a year's subscription of Emotive Pro. And so the 3rd place runner-up for the 2023 Student Club competition is Neurotech at Davis. Congratulations, well deserved. So let's check out the project video to showcase what they've worked on.
Concentration loss is a prevalent issue for many people and can decrease productivity greatly, especially for students. Hence, we are proposing an EEG-based BCI that can track and alert user when there is a concentration loss. We are tracking concentration level by monitoring a common indicator of focus, which is the beta wave. Then, when the user starts losing focus, our device will send a real-time haptic feedback, which is a small vibration in order to alert the user to stay focused. Our goal is not only to help users maintain their focus and increase productivity, but also empower them with self-awareness and self-regulation. In addition, thanks to the device user-friendly and non-invasive nature, it can be used in a variety of settings and for various users with various needs.
Hi, so our project uses the OpenBCI wet electrode EEG in order to stream brain frequency data to us in real time through 10 electrodes. So since we're trying to measure student concentration and focus during study sessions, our electrode placement focuses on 2 main regions, with the first one being the prefrontal cortex, as well as the frontal, occipital, and parietal lobes. And so what we're specifically looking for in these recordings are the difference between the alpha and beta waves, as well as the band powers. And so the way we originally defined concentration was through our initial recordings using the OpenBCI focus widget. And so what this does is basically just tell us when the user is focused versus when they are not. And so the way we used this was going into our recordings to see when the user was focused, and from there we could generate our own threshold based on the average of the band powers. Now I'm going to be talking a little bit about our data streaming. So we use the Python library MNE to visualize and analyze our data straight from the EEG itself. And so doing this, we can look at our recording and get rid of any noise by applying a low bandpass filter. And so since MNE doesn't work in real time, we also use the library called BrainFlow in order to process our data in real time, as well as work with our classifier.
Let's talk a little bit about the classification and processing aspect of our project. During our project, we wanted see a good metric to be able to identify when a user is focused and when they are unfocused. So during our experimentation process, we saw that when a user is focused, these bands, the alpha waves, the beta waves, and the gamma rays, these specific bands start acting up very specifically. The beta wave band will always stay up on top, and the alpha and gamma waves would fluctuate very violently right next to it. And when the user is not focused, these three bands would fall down or act more fluctuatively, and we would not be able to find any kind of regular pattern with them. And that's when you can classify that the user is unfocused. So what we did is we decided to print out the raw values for these bands, which you can see over here. And we decided to create a threshold-based classifier that can identify when exactly these bands are up and when exactly these bands are down. So what our program that we wrote does is that it looks specifically at these three bands, and when the user is focused and the beta wave is high up and these two are fluctuating, it captures that and classifies that as focusing. And when these three things are going haywire, as when the user does when they're not focusing, then it classifies that as not focusing, which as you can see is represented right over here, and their corresponding values. As such, we're able to classify focused and unfocused user behavior, and our project works using that. Thank you very much.
All right. Yeah, so the way our program communicates with the OpenBCI is using a dongle. The Cyton board is actually communicating directly with the dongle that transmits all the information through a program called BrainFlow into a Python program, analyzes all the system using PyQt5, and that communicates directly to the Arduino. We use a library called Arduino with our Python program that directly communicates with another piece of code called using the Arduino IDE. Go for it. Right, so as I was explaining earlier, our program basically starts with Python that we connect to a piece of Python code and specific serial port that connects to the Cyton and the board ID. As soon as I run it, our GUI that we created ourselves would pop up, connecting directly to the Cyton board. This is what it looks like when none of the electrodes are connected. So it's just going to be raw sample data. It will fluctuate based on the stimulation to the electrode entry points right there. If you look right here, our Arduino is actually connected directly to the PC using a USB port. This is exactly the piece of code that we are using for the Arduino, and this is the Python code that we're using. When we connect to the Arduino actually is consistent of two different parts. One part is the LCD and the buzzer. The LCD and buzzer both are connected by this specific area of the pin section, which is going from ground all the way back to pin 3. A lot of the connections are directly to the LCD, and there's specifically 3 connections to the buzzer, and the ground and power cords are right here. There is a ground that connects directly to this breadboard, which connects to a battery pack, and the information part of this breadboard is connected to this side of the pin board. Not much of the battery. It has its own separate battery component and special wiring that connects to the motor when the motor is attached. If you look right here, we could see that the Arduino code is a very simple code. It's a giant if-else loop, which basically is taking one piece of program, which is specifically that string. If that string is consistent of digital write 14.1, that means that the user is unfocused, and it would essentially print that. If it's not printing that, if the program is responding with a digital write 14.0, that means the user is focused and the LCD screen will adjust accordingly. The way that is actually given out is using this specific piece of classifier that analyzes the hertz between 15 and 35 in this case, and it sends digital 14.1 if the user is not focused, and digital write 14.0 if the user is focused. Thank you so much.
During the trial, when we used BCI in real time during a learning session, We aim to have each learning session to be 10 minutes of reading or studying. For testing the classifier, we made sure the user was focused on the material, uninterrupted for 2 to 3 minutes, and then interrupted the focus by instructing them to look up and talk to someone. The program we used detected beta waves in the band power and updated a counter, which will continue to increase until the user refocuses. We adjusted the counter for different users depending on how long they wanted to receive feedback. It would send a message to the Arduino to trigger a haptic motor, and the user would be alerted to refocus their attention on the material. By using the haptic feedback, the user can effectively refocus their attention on learning and continue to stay concentrated during their study session. Moving forward, we plan on testing the project on longer learning sessions to accurately detect the loss of focus. We would also like to test this with more students to see if the haptic feedback is the best notification system for telling the user to concentrate and refocus on the material.
Hi, so now we're going to be presenting our live demo for our project. So we have our subject here, Raj, and what he's going to be doing is he's going to be reading his textbook for about 2 minutes, and then we're going to have a third person come and interrupt him just by saying hi, getting him to look up. And so right now we have our electrodes placed on the head with our hardware right next to him. And so what we have in there is our Arduino and our haptic device, which will activate when he loses focus after a certain amount of time. Like we mentioned earlier, this is a time that can be adjusted based on the user. And we also have a fan which will operate when he is focused, and this was just something we added onto our project. And to the left of here, we have our classifier in the back, as well as the visualization of the data. So we can look at each electrode channel as they're going and the band powers that are being used. So now we will begin.
Hey Braj, how you doing, man?
Hey, pretty good, man. How's it going?
That's good. What are you studying something right
Yeah,
now?
yeah. I'm actually
Oh,
doing my
nice.
anatomy right now, studying
wow.
for the finals. Yeah.
Perfect.
Okay. And next up is our second place runner-up. This team will receive a G-Tech Unicorn Hybrid Black Bundle. And without further ado, our second place runner-up prize goes to Trident Neurotech. Congratulations. Let's check out their video to see what they've worked on for this year's competition.
Hi, we're Trident NeurotechX, and today we bring to you our latest project, the AeroMouse, an EMG mouse.
You may be asking, why do we even need this technology? What's wrong with the traditional or even the ergonomic mice? Well, many of us spend countless hours on our computer for work, study, or leisure. This prolonged use often leads to issues such as hand cramping, neck strain, and overall discomfort. This is especially trying for individuals with limited mobility, such as those with carpal tunnel syndrome, repetitive strain injuries, or even conditions like Parkinson's disease. In recognition of these needs, various solutions exist, but they can be prohibitively expensive or at times difficult to use. With the AeroMouse, we aim to alleviate these problems and make technology more inclusive.
But what even is EMG? Well, EMG stands for electromyography. It's a technique that measures the electrical activity produced by our muscles by placing sensors on the surface of the skin. The core of our project is cutting-edge blend of electrical, biomedical, and computer engineering.
The design of our armband is based around a special configuration of electrodes, concentric ring electrodes. This category of electrodes allows for better spatial resolution while keeping the cost and radius of the electrodes minimal. While researching them, we found several different types of concentric ring electrodes, so we did a deeper dive into a few that seemed to fit our needs.
We decided to experiment with bipolar and tripolar electrode designs, which had 2 and 3 rings respectively. We looked at 2 different sizes in each category, including an 8mm and a 16mm diameter. We also experimented with linearly increasing the spacing between the rings, such as in this model, and we also looked at a design that had constant ring spacing, but a widened outer ring. We laser cut these electrodes from stainless steel. So our first prototype relied on attaching the electrodes to the skin with tape. We wanted to make this easier to use, however, and have the electrode placement be more consistent, so our next prototype included an armband with elastic and Velcro. Here, we relied on just the pressure from the armband to keep the electrodes in place and in contact with the skin, but we found that the signal quality wasn't as good. To remedy this, we added a tape backing to each electrode on the armband and found that this significantly improved signal quality. Our next model was inspired by watch bands and Crocs. We called this design Grid and Gibbet. It allows us to optimize the positioning of the electrodes during our research and design process. Initially, we planned to 3D print this flexible gibbet piece using a flexible filament, but we learned during the process that this compromised the integrity of the material, so we pivoted and chose to laser cut from a silicone sheet instead. The numerous positions available on this model allow us to easily fit the band to multiple individuals. We decided to use KD tape for the final model, as it has been widely used in EMG research to attach electrodes to the skin due to its flexibility and for its adhesive material. It also helped us reach our goal, which included using accessible and affordable materials.
Connecting the tripolar electrodes to the Cyton served to be a little more complicated than connecting conventional bipolar electrodes to the Cyton's channels. Since the electrodes rely on the potential difference between center to middle and center to outer ring, we had to use the measured voltage of the center ring twice. We looked through the Cyton documentation, dove deeper into the individual chip specifications, and spoke with a group that had previously worked with the Cyton board, and came to the conclusion that we could split the wire from the center electrode to the negative inputs of 2 channels, connecting the outer and inner electrodes to each channel's positive input. This allowed us to take advantage of the Cyton's built-in ability to take the difference between signals. The final step is integration of Aramus components with a custom low-cost amplifier we nicknamed Tinny. This amplifier is designed to provide some of the same functions as common biosensing boards available, such as OpenBCI's Cyton board. On the board, there's an instrument amplifier for each channel, built-in hardware for post-processing of the raw signals, buffering amplifiers, and a microcontroller. These components work together to amplify, filter, and convert small analog biosignals into computer-compatible digital signals for any biosensing hardware, such as Aramus. Although we built and tested Tinny for a 2-channel system, our biggest challenge was to expand the number of channels to integrate the board with Aramus, an 8-channel system. Unfortunately, the iterative design process coupled with shipping times and part shortages were unable to fully integrate this board with Aramus within this project timeline. Because of this, we decided to complete the system with the OpenBCI Cyton to develop the product to an end.
Data processing includes pre-processing and feature extraction. We compute the tripolar Laplacian for each electrode using the middle and outer components of the electrode. The concentric ring geometry of these electrodes in combination with Laplacian filtering helps to identify the potential source with increased spatial resolution. Then we apply DC offset removal and bandpass filtering to eliminate low and high frequencies and increase the overall signal quality. To classify behavior based on these filtered signals, we then computed sets of features based on 200 milliseconds of sectioned raw data. These features were computed in real time and used to classify signals into various categories using machine learning, which Aiden will describe next.
We initially trained a support vector machine on the aforementioned time domain and spectral features of the signal to classify between periods of rest, clenches, and snaps. However, we realized that that would take time to collect data and train a model for every single individual user. In the spirit of accessibility, we wanted to make it as simple as possible to perform standard computer functions. We took inspiration from Psionic, a cutting-edge prosthetics company, and used a threshold to detect muscle flexion. We experimented with different features and found that the mean absolute value of the signal was the best metric for consistently detecting clenches and snaps. We still have an option to train a support vector machine to classify between clenches and snaps, which are then mapped onto left click versus right click to control the computer. However, we found that the threshold system works for most ordinary computer use, and it can always be easily recalibrated based on voltage variations between users and sessions of use.
At the heart of our system is robust and efficient software, which interprets both accelerometer and time series data from the EMG armband and translates them into accurate computer control. In our main file, we use an LSL stream to get EMG data from the electrodes and hand acceleration data from the Cyton's accelerometer. Each stream is fed into its own thread where sampling, processing, and GUI calls can occur independently. This optimizes speed and synchronization of the cursor outputs. Each thread follows a similar pipeline. Data is pulled, processed, and its output calls a change to the cursor, either movement or a click, to the Pi Auto GUI package. However, moving the Cyton board inherently creates noisy signals and may lead to false positives. To mitigate that, when the cursor is moving above a calibrated speed threshold, the clunch detection deactivates to avoid unintentional clicks. It was an interesting but complicated problem to work out the physics of using accelerometer data to estimate displacement in space and move the cursor correspondingly. We found that an elegant and user-friendly solution is to move the cursor proportional to hand tilt. This enables cursor control without imposing restraints on hand position or requiring excess motion. Lastly, this script allows the user to customize their experience with a command line feature to adjust sensitivity and timing to keep the spirit of accessibility and human-centric design. Now, let's look at the Aeromus in action.
So here is the Aeromus armband. Firstly, the user will put on the armband and make sure the concentric electrodes are secure. After turning on the OpenBCI equipment in the LSL stream, we'll turn the Aeromus software on. Here, we see that the software has customizable functionality for sensitivity and timeout. Now we see that when the demonstrator's wrist tilts, the cursor moves accordingly, and in order to click, he clenches or snaps.
Our aim is not just to create, but to inspire. That's why we will be open sourcing our project so that others can learn from it, reproduce it, and even build upon it. In our repo, we have in detail the specs for the Aeromus, a README for setting the software up, and package listings for ease of implementation.
When developing neurotechnology, it is important to consider the downstream consequences and ethical issues that may arise. We like to imagine that we are a company introducing a new product. Naturally, we want to maximize product performance and usability by collecting all the data we can. However, as users, we would also want to be sure the privacy and safe handling of our electrophysiology data. That is why we would securely store anonymized user data and offer an opt-in option to share data in exchange for compensation. As brain data is increasingly collected and commodified, it should directly benefit those who contribute, and they should be compensated for the value they provide to the community of users. Additionally, an important but underlooked aspect of NeurotechX is being honest about a product's capabilities and limitations. Our current iteration of Aeromus can move around a screen and reliably click, however it lacks the ability to scroll and the movement can be slow and choppy. Of course, no product is ever perfect, and there will always be limitations that must be communicated so potential users can evaluate whether a given product is right for them.
We appreciate your interest in our journey. We're excited to continue to innovate and bring accessible, user-friendly technology to all, as well as improve upon Aeromus's current limitations.
Moving forwards, we plan to decrease the cost of Aeromus and increase ease of use through more efficient, robust armband design, integration of our TINI technology, and expansion of computer functionality to fill the niche of a computer mouse.
Stay tuned!
Great work, Trident, on your Aeromus project. All right, so that takes the third place and second place winners. And next up, we're going to announce our grand prize winner, who will receive a GTech Unicorn Hybrid Black Bundle from GTech, as well as a 1-hour product consultation with NTX services, and bragging rights as the 2023 NeurotechX Student Clubs Competition first place winner. And that team is Neurotech SC. Congratulations, well deserved on the grand prize winner. Let's see what the first place project video looks like.
Hi everyone, we're Neurotech SC, the UC Santa Cruz chapter of NeurotechX, and our project this year deals with phoneme recognition using FEMGs, which are just facial EMGs that go along the jawline. And my name is Navriti Babaraju, and I'm the president.
I'm Matthew Sardi. I'm one of the administrators.
I'm Chris Bjordal. I'm one of the hardware team co-leads.
I'm Dennis Costa, the data and machine learning team lead.
I'm Rico Rodriguez, and I am also an administrator and also the software team lead.
So why phoneme recognition? So first, just introducing what phoneme recognition is. Just it recognizes the small units of sound that are present in the alphabet. So one of the major goals that comes from this is word recognition from facial EMG signals. And then this would allow for subvocal speech transcription for communication. And then a couple applications of this are for people with disabilities, since not all people are capable of producing vocalized speech. And then another application would be human-computer interfaces, which would allow for technological progress and exploration.
Regarding the neuroethics of our project, data ownership is only given by consent of the user. Data acquisition and bias, we try to unbias the data by diversifying where we collect the facial EMGs from. But for our final model, the data was recorded using Chris's face, so that might be difficult to generalize. Technological use and ethical considerations, it's open source, so it's able to be replicated and verified from whoever has access. For the overview, we will start with the face. There we will collect EMG signals through the OpenBCI open source Cyton board, the picture there. There we also see Chris with the dry electrodes on his face. The data will then be passed over to ML. Here we see a picture. This will then be sent to the software team where they will predict the phoneme in a nice graphic user interface.
Okay, so first we're going to go over hardware. So for our job as the hardware team, we recorded data for the machine learning and data team to implement into a model. The procedure for recording was intricate and precise to utilize the muscle groups we used to the best of our abilities. And the muscle groups we used were the four shown in the picture on the right. These muscle groups gave off the best activation using the BCI board, especially for phoneme recognition. For the actual procedure, we had the board set up with a button and a microcontroller in between them. The breadboarded button was used to mark recordings. The microcontroller was used to connect the breadboard to the OpenBCI board so that it was all in one place and it was streamlined. The board itself, we had 4 channels set up, each having a dipole so that we could have 2 electrodes per muscle group, and a 5th channel as set as the bias so that there would be noise cancellation and more conciseness, especially for 250 hertz, which is what most areas and technologies use. For the mask, due to time constraints, we weren't able to implement the mask, but it would have been useful to have, especially for more accurate and efficient recordings, and especially so for more diverse groups, because the mask would have been set up as variable sizes, as you can see in the top picture. Variable sizes for variable faces, variable sized muscle groups, etc.
And so moving on to the data and machine learning aspect of things, after the hardware team collected various data sets, we would get a CSV file with it. And it basically went first, we got like the first 5, and then we chose 22, and eventually we got to all 44 phonemes. As well as with the final recordings with the 4 muscle groups, we basically used, we recorded the phonemes as well as some words, sentences, phrases, and a paragraph of text. A brief overview of the pipeline would be that we first filter the columns to get the necessary ones that we use. We remove the outliers and then use min-max normalization, which you can see the effects of on the right side of your screen, showing the 4 muscle channels and then the 5th button channel that we use to actually mark the segments, which we identify 10 segments per phoneme, 44 phonemes, so 440 segments total, as you can see at the bottom of the screen, with some other statistics about those segments. Then we use a sliding window technique to generate equal-sized training examples from those segments. And we experimented with different window sizes like 5, 10, and 30 values. And using those as training examples, we made an X train and Y train with the data and then labels into a NumPy format that we could then pass off to our machine learning models. And within machine learning, we took that data. We first considered the use of a TMC VIT architecture, which used transformers and convolutions and temporal multi-channel features, but it ended up being a bit too complex and overkill for a problem like this. So we switched to an LSTM RNN type architecture, which was more simple and surprisingly effective for this problem. So we decided to stick with that. As we got those data sets from first hardware, then we would process it, and then to machine learning, we kept basically the same network hyperparameters and architecture, and would just experiment with different small changes to see their effects. We did a standard 80-20 split. We used a sequential model with the convolution layers, LSTM layers, and fully connected layers. We experimented with a variety of model sizes ranging from hundreds of thousands to millions of parameters. And we eventually achieved 98.1% accuracy on test data with only about 200,000 parameters, which was very impressive and efficient. And as you can see, there's the loss and accuracy graphs where loss should be trending down, accuracy should be going up. So that looks good. We use various techniques such as dropout to prevent overfitting. And there are some data concerns whether training on data that is singular phoneme pronunciation will actually transfer over to predicting phonemes within continuous speech. But that is something we have addressed. And in order to actually evaluate our model, we use something called a confusion matrix, which basically shows the rows are the actual phonemes, and then the columns are which phoneme is predicted. So along the diagonal, those are true positive predictions, which is good. Outside of it is bad. As you can see circled there, 6 of the silence phonemes were actually predicted as EHs, so that can give some insight on where the model or the data might be lacking.
Now moving on to the software aspect of this project. As for our software team, our responsibility was to connect the machine learning model to a user interface and to record data. We weren't able to fully realize our initial plans for implementing a user interface due to limitations with how the model was trained and how it behaved. For our proposed architecture, the plan was to have an OpenBCI EMG data stream to the machine learning model, which had 2 threads, one for listening to that data stream and one for classifying phonemes and sending them to the user interface. We were going to have the classification model and the user interface in a Docker container to streamline deployment and development. As for our proposed user interface, which again was not realized, the plan was to show a live transcription over 10-second intervals to the user. The user would then be able to classify whether the prediction was correct or incorrect, and the result would be recorded into a database with the prediction and the user classification. For the future, if this was realized, the plan was to pass this prediction to another machine learning model to then predict text and display that to the user as well. As for what we tried for our user interface, our first attempt, we attempted to make a web app using Flask and Python with our machine learning model and GUI in separate processes. The cause of this is that we would need a WebSocket to pass data back and forth. Not everybody was familiar with creating an API, and a bit overkill and unnecessary for our use case. And we would use MongoDB to store the data. For our second attempt, we used Python with tkinter and our machine learning model and user interface in the same process. Now, this came with benefits such as tkinter comes with the standard library for Python. There's a lot less overhead with having a web service up. We would have shared variables instead of having to send messages through a WebSocket. It's simpler and easier to learn, but the cons of this was that we weren't able to containerize this due to limitations with tkinter. And likewise with the first attempt, we would also be using MongoDB to store our data. And so now moving on to our demo.
Here we have a few pictures of the data collection setup where the electrodes are placed and the various hardware. And we have a video of one of our recording sessions where we record 5 phonemes, a word pronunciation, and then a test sentence that contains lots of variable phonemes. As you can see, the recording starts and the OpenBCI interface shows the signals. as the subject, Chris, pronounces those phonemes with his finger on the hardware button, pressing it down during the moment of pronunciation in order to mark it within the actual data.
The quick brown fox jumps over the lazy dog.
Some limitations regarding our project is background noise and spiking caused from electrode placement error led to wrong or just incorrect data. To correct this, we would require new hardware for more accurate and efficient data collection, such as replacing our dry electrode method with wet electrodes, the not actualized 3D printed mask, or FPGA board. More data collection would lead to better model performance, and ideally a streamlined recording protocol would allow for more effective and accurate recordings. Once this is all complete, we would finish by integrating the model and data processing into the live transcription app. Thank you guys for listening.
Great, amazing demonstration, Neurotech SC. Well deserved for the first prize win of 2023 Neurotech Student Club competition. So yeah, so far we've seen some great projects. We'd like to congratulate everyone, but our last prize that we're gonna just go over is the NeurotechX prize. And as I mentioned before, this prize is brought to you by Neurable. And for this prize, the student club team who scored the best for neuroethical considerations and will receive 3 early access Neurable headsets by the end of this year is Trident Neurotech. Amazing work. And we'd like to congratulate this year's winners of the 2023 Student Club NeurotechX competition. As you saw, in third place, we had Neurotech at Davis. We had in second place, Trident Neurotech. And in first place, our grand prize winner, Neurotech SC. And Trident Neurotech actually took the NeuroEthics prize sponsored by Neurable too. So yeah, overall, everyone did an amazing job. We were blown away by your projects. We loved all of the winning projects, of course, but there was some amazing projects that didn't, make the top 3 spots, but they're all amazing projects nonetheless. And obviously, we wish everyone could be winners, but some extra motivation for next year's competition. And yeah, competition is fierce, but let's see what next year brings too. So yeah, to the winners of this year's competition, we'll be in touch to get you the prizes. And to all the student club teams, great work, everyone. Amazing projects. And we hope that you're feeling inspired by the amazing work our student clubs have put forth this year and by the student clubs initiative in general. So please check out our website for more information. If you have any questions or you'd like to sponsor our upcoming student clubs initiatives, please shoot us an email at studentclubs@neurotechx.com. And be sure to check out our NTX Student Club website for more information there. And with that, we'd like to say thank you for your support of the NTX Student Clubs initiative. Everyone, we couldn't do this without you. So make sure you stay connected, and if you're not already, make sure you subscribe to our monthly newsletter and join our amazing NTX Slack community for some great discussion and networking. And if you're a student club and you want to be part of next year's competition, make sure to email us and secure your spot. And again, for any student groups out there that are thinking about becoming affiliated with NTX but haven't officially done so, please email us at studentclubs@neurotechx.com. The sooner you reach out, the sooner we can onboard your team and make sure we can get you into next year's competition while registration is still open. So we'll be announcing next year's competition timeline soon, so please reach out to us for more information. And again, as I mentioned, we'll be sending out a post-event survey to everyone who attended today's ceremony. So if you can please fill that out, it'd be very helpful. Again, we're a nonprofit neurotech organization, and we appreciate all your help and support, and we couldn't do this without you. So be sure to check out our YouTube channel for the rest of the amazing projects. All the projects from this year are posted here. You can check out the previous year's competitions for some inspiration. And yeah, we hope to see everyone participate in next year's competition, and we can't wait to see what you will work on. So with that, we'll close off the 2023 NeurotechX Student Clubs Competition Award Ceremony. And make sure to keep in touch. Follow us on social media for upcoming exciting events. Thank you.